Light. Ever since the dawn of humanity, we have searched for light to increase our productivity and knowledge. That search for light led to the discovery of fire, which was followed by candles, gas lamps, incandescent bulbs, fluorescent lights, and finally, light-emitting diodes, LEDs, the most efficient source of light we have created so far. LEDs are used in all modern electronic devices, and it seems that the trend of light evolution is heading towards energy efficiency, that is, less heat and brighter light. And now, through something called the landscape function, we can make our brightest light even brighter. To understand its significance, we must first examine the structure of LEDs. LEDs are essentially composed of two parts, the N-type layer and the P-type layer. The N-type layer is the higher energy layer with a surplus of electrons, while the P-type layer is the lower energy layer that has an abundance of empty spaces we call holes. When there is a current applied to the LED, the electrons and holes merge at the junction of the N-type and P-type layers. At this point, the electrons go from a higher energy state to a lower energy state, and the difference between the two energy states is emitted as visible light. So ideally, if all electrons of movement combine with holes, almost all of the electrons will convert to light. But reality isn't like that. In reality, there are some electrons that simply don't combine with holes, and their energy difference is not enough to produce visible light, which is just a waste. The reason why this happens is because of a phenomenon called Anderson localization. Electrons exhibit properties of both particles and waves. In a material with regular atomic structure like a crystal, then waves of electrons may propagate freely. But in a material with irregular atomic structure like industrial semiconducting alloys used in LEDs, waves of electrons may run into an area where they trap or localize themselves, like how sound waves resonate in a seashell. They will eventually fade away and cancel each other out, like how mixing many paints of different colors will result in a black paint. This wastes energy and produces heat instead of visible light, shortening the LED lifespan. Though this is a simple concept, the calculation of the location and energy levels of localized electrons has not been solved since the discovery of Anderson localization 40 years ago. But very recently, mathematician Svetlana Mayboroda and physicist Marcel Fellowci created an equation that does exactly that, the landscape function. The landscape function interprets a material according to its structure and divides its domain into small subregions. Then, it calculates where electrons will localize and what states they'll be in according to different amounts of energy provided. Finally, it visualizes those values by forming a kind of a terrain, thus the name, the landscape function. Using the landscape function, engineers and physicists can now find and fix the faulty regions which waste energy and perhaps even decrease the energy loss to the theoretical minimum. Through the combined efforts of physics, mathematics, and engineering, we are one step closer to a brighter future.